So, hello everyone, and welcome to monitoring Kubernetes Drupal clusters using distributed tracing. If you're hosting any Drupal sites on Kubernetes or are in the process of moving to a Kubernetes cluster infrastructure, this session is for you. So first, a little bit about me. I've been working for Acquis since 2011, based in Lisbon. I am now managing the DevOps SRE teams. I co-authored the Seeking SRE book and also founded the Portuguese Drupal Association. Some fun facts. I have 2 kids. I started using Linux back in the 90s. At the same time, I was actually performing on stage. So here is the agenda for today. I will start with the problem we are trying to solve, and then I will be going from the monolith to microservices and distributed systems. Next, we will focus on the observability of distributed tracing and the solutions that we have. We will end up with 2 demos and how to get value from the distributed tracing in Drupal. So, what problem are we trying to solve here? Why distributed tracing? I start with this picture. If you've already researched cloud-native applications and technologies, you've probably came across the Cloud Native Computing Foundation CNF landscape map. And surprisingly, the sheer scale of this map can be overwhelming. So many categories and so many you don't see the slides changing? Can you see it now? Oh, interesting. Can you all see the slides now? Okay, let's try this again. Okay, so I start with this picture, as I was saying, and surprisingly, the sheer scale of this map can be overwhelming. So many categories and so many technologies. And the fact that this is a huge part of Drupal hosting sites today, working with distributed systems, there are microservices using Kubernetes, containers, serverless, many things. That is a broad scope of combinations. So this challenges the old way we have looked at observability, the way we use monitoring and do troubleshooting of microservices. Let's see if the slide changes now. Did it change? Okay, great. So I'm trying to adjust here the on-air. Looks like it doesn't like the fact that I have several windows. So I'm trying to adjust here a little bit. Bear with me. Okay, cool. So to make it clear, let me tell you my personal story with tracing and debugging systems for over the years. It's pretty much what you see in these pictures, except it would be, of course, with Drupal 9 last year. I would be working on the debugging side on a few servers or spinning up a local environment. But in any of the cases, it would be always be looking at one thing, one console, one unified service that would handle Drupal from, and then I would just need to watch the database, the file system, the network for bottlenecks, errors, and other weirdness. While using the usual tracing tools like XHProf, BPF, strace, or sysdig, they will work with monolithic systems, of course, but such is not the case for microservices distributed systems. Exceptionally, in the case of eBPF, that can be used in tracing Kubernetes. So That meant that I, as an engineer with the direct access to those systems, was in control of all of that. And my responsibility was clearly defined and visible. But that is not the case anymore. In this new world, the service that you can control has a lot of dependencies that you're also responsible for, but have no direct control over. It quickly becomes unrealistic for a single human or even a group of them to understand enough of the services that are in the critical path of even a single request and continue maintaining it. This becomes a recipe for stress and burnout. Still, are you still not convinced of why we need this? So the answer is simple: root cause analysis. Imagine you wake up by an alert at 2 a.m. and a request involving 5 different Drupal sites or microservices is failing repeatedly. You're jumping into the logs, still trying to open your eyes, looking for the errors around the time of the alert, but the stream of data is too big to figure out what happened. It just takes too long. So by using distributed tracing, you can find the first service that failed, get the logs from that failure, and find the root cause quickly. There is also complexity of a Drupal application running. There is also the complexity of a Drupal application running on my simple Kubernetes setup here. Last year, Luca Lusso presented a very interesting observability session at DrupalCon Amsterdam and proposed the creation of a Drupal observability module, which we will talk a little bit more about later. I believe that our community is still not aware in full of this issue when it comes to Drupal reliability and why we need to solve observability. Therefore, this session specifically, I propose to do exactly that, raise the awareness. So what happened? How did we got to this situation? So the traditional application architecture is monolithic, as we know. It's a convenient single unit that contains all of the functional components, including database operations, business logic, background processing, etc. They are all testable and deployable together at the same time and running on the same servers. However, these benefits carry their own difficulties, like having a single shared language runtime, having to manually deploy the entire application when you only have a need to make a small change, manual replacement of the scaling, and no isolation of resources or failures. On the other hand, the microservices approach designs applications as a set of small services. So every service is a separate application with its own framework, programming language, and database. They're all developed and deployed separately from other services. They communicate through inter-process communication protocols like HTTP, AMQP, or binary protocol like TCP. So the microservices concept allows working on different services independently without impacting the work on the other ones, on the other components. Service-oriented architecture became a thing partially because computers got cheaper, so we had more of them. It made more sense to make use of multiple cheaper compute machines. However, microservices are not simple to develop because they had the complexity of having to create a distributed system. They neither simple to deploy because of the operational complexity of deploying and managing many services, and also not simple to scale because instead of just scaling n monolithic applications, you would be scaling n versus n services instances. Honestly, microservice sounds like a really bad idea, except for all of the other good stuff like easy for engineers to understand, able to maintain code quality and modularity over time, no IDE overload, easy to continuous deployment, and for large application, less deployment risk and multidimensional scaling. Also, the team autonomy between teams and the ability to adopt new technology. So in summary, if we look at Kubernetes, there are clear advantages like scalability, flexibility in terms of the tools and technologies, increased productivity, allowing teams to work in different components, easier communication in distributed teams, maintenance, since detecting an error and repairing it gets done in no time. However, when you have a lot of building blocks, it can be tricky to discover exactly where the problem is arising. That's why full observability and monitoring tools need to be in place. So at the end of the day, just be aware that when people replace that monolith they have in-house with the microservices, they are often caught by this surprise with this problem. You know, like every outage could be converted into a murder mystery. So distributed systems and microservices. For this intrinsic relation, I invite you all to read a great book, Distributed Systems Concepts and Designs. It was long before Kubernetes, or even longer, or even before the internet as we know it today. In 1988, George Coulouris from the University of Cambridge published the first edition of this book. And the challenges mentioned here are similar to the ones we face today. Let's see. So these challenges are heterogeneity. So they actually use a variety of different networks, systems, hardware, and languages. Openness, to be extensible with documented interfaces, with document interfaces of each component. Security, so the encryption for adequate protection of resources and network messages. Scalability, for frequently accessed data needs to be replicated around, and failure handling. So any process or computer in the network may fail at any moment independently of others, and they still have to be able to do their work. Concurrency, each resource must be designed to be safe in the concurrent environment. Transparency means that the distribution should be invisible to the user or even to the developer so that they actually can focus on their tasks. And finally, quality of service must be included with parameters related to performance, security, and reliability. As an example, here you have a visual representation of Uber's microservice architecture and kind of hypothetical transaction. There are quite a few challenges with this design. In order to run these microservices in production, we need an advanced orchestration platform that can schedule resources, deploy containers, autoscale, and so on, which is why projects like Kubernetes became so popular. Microservices need to communicate and know how to find each other on the network, how to route around problematic areas, how to perform load balancing, how to apply rate limiting, and so on. So also here, the latency may also increase. Finally, the observability of the system is dramatically reduced if we try to use traditional monitoring tools. I'm pretty sure some of you already are running Drupal on Kubernetes, right? So if you can use chat, if you're using Drupal on Kubernetes, just put your, just say yes there. So major things to consider are declarative deployments, enabling rolling and fixing deployments with the blue-green strategy or the canary releases, hybrid workloads, and all that sitting on top of a cloud-native architecture, as we see. Any architecture decision involves a trade-off, you know, like, and there is no free lunch with microservices, honestly. They come with a significant operational overhead that requires sophisticated infrastructure, automation, and monitoring. This is actual data from the Global Microservices Trend Survey, which is really interesting. We can see here from the survey that the growth in use of microservices is remarkable. But many organizations are still starting, and it's not expected to slow down. Almost all, like 98%, expect microservices to become their default architecture. And the majority, like 86%, expect that to happen within the next 5 years. So the top two motivation drivers are agility with 82% and scalability with 78%. And here it is. The most common issue reported by 56% microservices adopters, also Kubernetes, is that each additional microservice just increases the operational burden. Other challenges include teams organization around microservices, like 47%, difficulties to find the root cause of the issue, like 45%, and lacking the need skills to build and manage microservice architecture, which is 45%. Among those that have microservices in production, there are 73 that report that troubleshooting is harder in the microservices environment. So now that we know our problem well, microservices observability, how do we actually solve it? We need observability tools that tell us the story about what happened to a request by answering which services did the request go through, what did every service, every microservice do meanwhile, what were the bottlenecks, what errors did happen, how different was the execution of that request, what was the critical path of that request, and perhaps most importantly, who actually should be paged, right? We don't want to page someone. Imagine it's divided between teams, or we don't want to page the wrong team. We want to know which team needs to actually be paged. Unfortunately, traditional monitoring tools can help here. So we'll need to monitor and analyze our application so any anomaly gets detected and rectified right away. The existing types of tools are listed here in CNF, namely logging, so tools to collect and event logs, monitoring, which are solutions to collect metrics, tracing that goes one step further than monitoring and actually goes and checks the propagation of user requests, and chaos engineering in order to identify weaknesses before they actually impact production. A proper observability of a system is based at least on these three pillars. So you have structured logs. In Drupal, we have a battle-tested library to do logging. It's called Monolog. I don't know if you guys know this, but it's actually very good. And then we have the second one is metrics. So metrics are a measurement at a point in time for the system, and you can use Prometheus, for instance, for that, which is open source and it's free, and Grafana. And then we have distributed tracing, which is the most most of the time is completely forgotten, which is the answer we are looking for in this presentation. Finally, observability should consist of logs, monitoring, and tracing events. With those, we will be able to understand our systems. It's the measure of how well internal states of a system can be inferred from a knowledge of its external outputs. So inside of observability, we want to avoid a thing called signal to noise. It's an issue, right? And it's by using distributed tracing together with all the other two pillars that we don't get lost in the noise when we are investigating an issue. So distributed tracing is getting a lot of mindshare lately, and is now becoming a new foundation of DevOps. Unlike traditional application performance monitoring, distributed tracing is intended to address the observability challenges and use cases in the new microservices world. And yeah, the big question is, why is it slow? So the basic concept of distributed tracing is actually very straightforward. So you have instrumentation that is inserted into chosen points on the program code, which are called trace points, and produces profiling data when executed. This profiling data is collected in a central location correlated to the specific executions or the request. And then it's arranged in a causality order, so you know which sync actually caused the other, and then it's combined into a single trace that can be visualized and further analyzed. Google Dapper, 2010, they have a design paper, which is the cornerstone of distributed tracing. So this paper actually explains how Google developed a production-grade tracing tool with 3 key goals behind it. First, low overhead. Second, application level transparency, scalability, and I would say also with the availability of a trace data in few minutes, really few minutes after the request. So that will introduce some terminology like trace. So trace is the description of the transaction. You have span, which is the operation representing a piece of the workflow. And then the span has a context, which is the trace identifying information of the transaction containing the trace identifier, the span identifier, and other useful data. And all of this is instrumentation, which is the process through which your application code captures and reports trace spans, and annotations, which live, sometimes they are called baggage. It allows the developer to enrich the trace with counters, with logs, and whatever data can help to investigate an incident. The Open Tracing API, which is a fairly new thing, provides a standard vendor-neutral framework for instrumentation. This means that if a developer wants to try out a different distributed tracing, then instead of repeating the whole instrumentation process for the new distributed tracing system, the developer can simply change the configuration of the tracer. So let's now see some distributed tracing solutions and actually a couple of demos. So we make this more practical. In 2016, both Google and Amazon announced the availability of Stack Driver and X-Ray and other in their respective clouds. And since then, a fairly high number of other tracing systems were created in open source, like Zipkin, Jaeger. We're going to actually demo Jaeger here, and so on. So for my first demo, I will use, let's see how this works. I will use Istio with its sidecar module. It's important to note that while I was preparing this demo, the MySQL sidecar is not fully supported for tracing yet. So this will probably be available in the near future. However, there are other ways of doing full tracing, and that's what I'm going to show in the second demo here. Let's see. So I'm going to speak to show the demo, but it's already recorded, at least the images. So can everybody see the okay, so I have two Drupal pods there, right, on my Kubernetes system here locally, and MariaDB also pod, and then I have the Istio system installed inside of this Kubernetes cluster, and I can actually see how the Istio sidecar injector is already configured in the default namespace there. The default namespace, as you can see there, is using, so Drupal is inside of the default namespace. So what we have here is the Drupal side on the right side, which is connected to those two pods. And now I'm going to generate a little bit of traffic, like maybe create here a basic page. Okay, I will edit again so I can just create more traffic, go back, and making here a real good test, which is going to available updates and checking manually. So this creates a request outside of Drupal. Let's see how that works. And then I go to the Jaeger user interface. I'll need to refresh this. Okay. So now I have Drupal default, which is the default namespace, and I have really a lot of traces here. Let's see the one that has most spans. So I have one here with 8 spans. Let's look at this one. And here I have something special. So it actually comes from the Istio mixer and then goes out from the Istio mixer. And we have 2 Drupal spans, which is interesting, right? So this one is actually outbound, which means something went out of Drupal. And this is, yeah, this one is inbound, which means it came from to Drupal, and then there's another one coming out of Drupal, which means this is the request I did to check the available updates. So it went inside of Drupal, and then the same request went out of Drupal. So it catched all of that. And I didn't change anything in Drupal in this case. Istio just creates this sidecars that go around Drupal, and you have the 2 Drupal pods there, by the way. And here we can see, we could actually compare traces if these were big traces, and then we can see the diagram that is created automatically from the pieces I have in my distributed system. What comes for free is, as I was saying, is Grafana. So if you install Istio on Kubernetes, you get immediately Grafana for free, and also you will have which brings interesting data, and also you have Prometheus that you can use immediately. Yep, and then this is the graph we were looking for. Okay, so this was my first demo, very quickly. For my second demo, I will use Otrod. It's an application implemented using Jaeger and the Go client. So the Jaeger has a lot of clients. We will talk about that after the demo. But you have clients for Go, for Java, for Python, for Node, for PHP, for Ruby, etc. We'll talk about that after the demo. So Jaeger is an open source distributed tracing system. It's able to collect and show the traces and analyze the application's behavior using the open tracing API as we approached before. The Jaeger agent is a network daemon that listens for spans sent over UDP, which it batches and sends to the collector, as you see in the image. The Jaeger collector receives traces from Jaeger agents and then runs them through the process pipeline. So let's see how this works. So here I have a bare install of the Kubernetes system. I don't have anything installed. I'm just going to install Jaeger. So I changed their files, their YAML files to actually be able to do this. So I'm now installing Jaeger and Otrod application. This is actually the service you see in the image. It's not all of the pods. They actually have a lot of pods, as we're going to see. And this is now appearing on the Kubernetes dashboard. And I'll just copy the IP of the application so I can have it 8080. So here's the application, and it just pertains to call rides on demand. So it's pretty much an easy application to do. So and now I'm going to put here the Jaeger user interface. 166.86. And as you can see, there's nothing here. Like, this is completely empty. I just installed it from scratch, and I have this client ID, and now I'm going to start and generate some rights demands on the rights, generating traffic, and just we have a lot of rights already. And we can actually see these calls coming from the logs if you use directly logs watching in Kubernetes, as you can see on the left, right? Which is interesting. So let's now go to the other interface. We'll probably refresh this, and you will see we have a lot of microservices components here. Let's go to the route one, and plenty of spans already caught by the Jaeger client. And here we can see there are two errors, and these two errors are related to Redis. So so you can see this is really easy to drill down and see which part of the microservice or the distributed system actually failed. And this microservice is the one that is having timeouts, as you can see in the logs there. So Redis timeout. Okay, so it actually increased and made the application went slow. By this time, I can just talk to the developers, or I'm the developer, and I can just go and try and debug furthermore with other internal logs or even internal tracing to see why is this slow, which queries did I actually fail, and I can connect that to this application. So the system architecture in this case, it's much more complex and goes, like you have the driver and you have Redis and you have the front end and the route and then the customer and then MySQL. and it's all connected to the front end, and you have all of the requests that we have seen up to now in Jaeger. Okay. So we now start to see how we can get value from a distributed tracing in Drupal. But we don't have a proper module yet, and this is actually one of the key things of this presentation. There are different Jaeger clients for PHP. The most complete one at the moment seems to be this one here. So the code is a little bit messy, but it works. And it goes like this. The main concept of the goal is very simple. We track our network requests to the PHP application by adding two dependencies to our composer.json. So it's Jaeger, PHP, and open tracing. Then in our PHP controller, we'll instantiate our Jaeger tracer, giving it the port of the Jaeger agent and the span context. From there, in the Jaeger dashboard, when we're calling Drupal as a PHP application, we should see the network going to Drupal. As I mentioned in the beginning, I want to call out to the initial brilliant work already done by Luca on the Drupal observability module called O11Y. I actually contacted Luso before this session asking permission to mention his work, and I will probably start working with him to contribute back to this promising solution. Meanwhile, tomorrow morning, you can join me at the BOF I created here on our DrupalCon, so we can start discussing a Drupal observability initiative for the ones that are interested in it. Of course, there are commercial solutions that work out of the box. They are not open source. For instance, the new Relics PHP agent now supports distributed tracing as of PHP agent version 9.8. The documentation there contains PHP-specific tips to enable distributed tracing for a PHP application like Drupal, and it works out of the box. Last slide, and just to name another offer between several other there. So Datadog also supports distributed tracing on PHP, also out of the box. The PHP tracer supports automatic instrumentation for several libraries, and it's actually really easy to configure. Okay, thank you. I would ask, don't miss the BOF tomorrow at 11 a.m. about Drupal on Kubernetes. That's going to be really fun. I never did a BOF online, but that's probably going to work well. And yeah, if you have any questions, let's talk about this. And don't forget to rate after the session. So let's see. I have one question here, and it asks, it's from Konstantinos, and it asks, for the Jaeger demo, is Jaeger plug and play with the Drupal app deployment shown in the first slides? I'm not sure I understand the question, but as I shown in the demo, you have two ways of using Jaeger. So Jaeger can be connected to Istio, right? So you have the sidecars, and yes, that is plug and play. Like as I shown in the demo, maybe it was not clear. You can just go turn on the Istio sidecar system to use with any application you have on that namespace. In this case, was the default namespace. And then any application that you run on that namespace, ICO will create a sidecar that will attach to that application, and we will be able to transmit all of the tracing to Jaeger. Okay. In the second demo, it's a little bit different. You have the client. So in this case, that's why the Drupal module is useful. The Drupal observability module is useful because you can actually use the module, put the module inside of Drupal, and the Drupal module will send via the application, the PHP client application, will send the traces and the spans to Jaeger. I hope that answered your question. So the second question is there performance impact of tracing, data protection, or should we only use it in the non-prod environment? Okay, that is a very interesting question. Depends on how you set it up. So the way you set up this currently, so it sends data via UDP and it's inside of the cluster. If you have your if you have your cluster open, you already have a problem. And that's not what we're looking to solve here. You should always have your cluster inside of the VPC or something that protects you from the outside world. So the connection that comes from the client to the actual Jaeger collector here is always protected, right? There is no way someone, unless you have a problem in terms of protection in your cluster, there is no way someone will see that. And then in terms of performance impact, depends. So ICO is a little bit heavy, but if you go to the PHP client strategy, then yes, that's probably not very heavy. I would prefer to have the client, the Jaeger client, working instead of using the complete ICO. But ICO gives you a lot of other benefits, like brings Grafana inside of it, brings Prometheus. You don't have to code any client, and it just works out of the box. So as long as you know how to install it. Okay. So okay, I'll answer this. So the two methods of using Jaeger. Another question by Konstantinos. There is a new one here. The two methods of using Jaeger that you described, ICO Drupal module, would they record the same traces? No, absolutely not. Because if you're sending some data that is internal to Drupal, you would have more detailed data, right? If you have data that is outside of Drupal, it relates more to the distributed system or distributed. In this case, it's more regarding the network and the system, but you can still see exactly where it fell because the connections will be recorded, and then you can just drill down with that. And then Nicholas Fruit has a question here, not a specific question about monitoring, but do you have best practices resource to deploy Drupal on Kubernetes? Well, I have my own files, but if you want something that works out of the box, you can just use the Bitnami Helm chart, for instance. Okay, cool. We're almost out of time. I think we don't have any other questions. Am I wrong? No? Okay, cool. So thank you all. That was it. I'm going to hope this ends. John is here as a volunteer. I think the session can just. Thank you, everyone, and don't Don't forget to join the contribution opportunities, also the contributor workshop, general contribution, and mentored contributions. Thank you all.